Welcome back to the course. So today we will try to gain some understanding how do we really do an economic analysis for an energy system. This methodology could be applied for any energy production pathway, not necessarily hydrogen, but this is something that we'll be using in the future classes. So how we'll be going in the future classes would be like we'll be selecting the different pathways for hydrogen production as well as transportation storage and trying to make economic models for us, try to see which are the areas which demand maximum amount of money where we could change the economic scenarios for the future to give us a better understanding. So in today's class we'll just try to get an overall understanding how can we make an economic analysis for an energy production pathway, and this is something that we'll be using specifically for hydrogen production and storage transportation, which we'll be learning in the future classes. So if you can go to the whiteboard. Okay, so the methodology that we are going to use for economic analysis was basically developed by ICI PLC, and it was developed long back for the chemical engineering operation, but as such that provides a good methodology for understanding what could be the production cost of a particular fuel or the energy consumption. So how we are going to do is, like, underlying formula is going to be the production cost is going to be an addition of three things: F, C and O. So what I mean by P is the unit production cost, by F I mean the feedstock cost for unit production, then C basically refers to the unit capital cost, and O basically refers to non-feedstock operating cost. So these are the few costs or the few major costs that you are going to encounter for analyzing the production cost. The major of course would be going to be the feedstock cost. What is the feedstock that is used for the production of hydrogen? So this could be natural gas if you are going towards production of hydrogen based on fossil fuels. If you are going towards production of so-called green hydrogen, the feedstock in this case would be electricity and water. What I mean by capital cost is the installation cost of the plant. So you might want to install a steam methane reformer, you might want to set up a big electrolyzer. So that is a one-time cost that is might be spread over a couple of years, but that is before the operation of the plant is being set up. And what I would want to see is how that cost is factored into the production cost. So normally what is being done is you use a factor like capital recovery factor, wherein you are basically normalizing this capital which is spread over the initial few years into the operational phase of a plant. And normally you are using a capital recovery factor taking into account time value of money. So now I am taking for granted that a majority of you students have done some kind of basic course in which you have understood the time value of money. If not, you can look towards other courses. There are plenty of available material that is available on the internet to understand the time value of money. So basically what we are going to do here is basically spread the capital cost throughout the production phase of the plant. So the capital cost that was spent during the initial installation when there was no production of the product is basically spread out throughout the production phase so as to account for it. And then beyond the feedstock and the capital, you would also need a good amount of labor, maintenance, which comes in the non-feedstock operating cost. So if I have to first estimate the capital cost, that could be done based upon the equipment sizing, but in most of the studies that we are going to take the capital costs that are directly available in the open literature. And further, it might happen that the plant size for which we are trying to estimate cost, they might not be available in the literature. So in that case, we can use a simple correlation which can go as is, like the capital cost for maybe plant 1 divided by the capital cost of plant 2, for which the cost might be available, can be given with the help of correlation in the form of capacity of plant 1 divided by the capacity of plant 2, and the whole thing is raised to power n, and the n here is basically the capacity factor. So normally it varies between 0.6 to 0.9, but 0.7 could be a good feature, and this basically brings in the element of economies of scale. So what do I mean by economies of scale? It's always cheaper to manufacture something on a large scale. So the bigger the size of the plant, the lesser the cost is going to be. Or it could be taken as other way around as well. If the plant we are looking at as is working at a lower capacity, the price or the unit production cost is going to be on a higher end. Further beyond this, we also need to understand there are factors such as the location factor. If I can go back to the slides. So when I say the location factor, like manufacturing something in India might not have the same cost as in the US. So what you see in here are typical like location factors for maybe India and Indonesia for some time back. So if you would want to manufacture something in India, that might cost almost 70% of that would have costed in the US. So if you are taking a cost for manufacturing a particular power plant in the US, you would have to factor in the location factor for a location like India as well. Another thing that you need to take into account is the cost indices. Now suppose the data that is available to you is for a previous year. How do you know what is the plant or cost of the plant today? Suppose the data that is available to you is for 2020. How do you normalize it for the year 2025 or 2030? For that we have a lot of price indices, and what you see in front of you are a few. So this is called the Nielsen-Ferrer price index, which gives you like if the index or if the price something costed like 1.9 in the past, what would it cost today? So normally this increases over the years. And another index that you might want to use is the chemical engineering plant cost index, which comes in almost again handy in this case. So you can refer to any of these indices if you would want to compare the capital cost, how that would have increased over the years. Further, like the capital cost of different plants have different components, like it's not just the equipment cost, but a lot of things go into it, and it depends upon whether the plant is handling just solids or solids plus fluids or just fluids. So based upon this, different factors are available which you might want to see. So going back to the whiteboard, let's first try to understand how am I going to convert the capital expense that is spent during the first few years of the plant installation to the rest of the plant operation phase. So for that we would be coming across something called as the capital recovery factor, and this could be the CRF. So normally a big plant would be installed in a couple of years. It could be 2 years and range to almost 5 years. So how do we basically bring in that cost? So if the total capital cost that is known to me, suppose a hydrogen plant has an envisioned capital cost of C naught, but it's going to get installed over maybe a couple of years, how do I spread that or understand the total cost, bringing in the element of time value of money? So the total cost taking into account the time value of money would be C is equal to C naught summation of S is equal to 0 going up till P AS 1 plus I, where I is the discount rate raised to a P minus S. So if I would want to tell you what does these elements mean, so AS is equal to the breakdown of capital cost, which basically means the percentage of capital that you are investing in a particular year. So suppose the plant is spread over 3 years, or the installation is spread over 3 years, so you might be spending 25% of the cost in the first year, 50% of the cost in the second year, and another 25% in the third year. So this is what I mean by the factor AS. P basically refers to the first year of production. That is when the production is starting. S basically starts to the general year of project starting. Scroll down. S basically begins, or we are going to begin from S is equal to 0, and the year in which S is equal to P, the production has or the construction has completed. It basically means and finally I is basically a discount rate to bring in the time value of money. For any of you for which the time value of money is a new concept, I would again request you to go through any of the basic engineering economics course, which will give you or try to like bring out this concept in much more detail. Now this is with respect to understanding the spread of the capital expense over a couple of years. So herein is in the slides in front of you is basically giving you a basic bifurcation of the installation of plant, which we will be assuming. So if the plant is getting installed in 1 year, possibly we are assuming that all of the investment happens all at once. If the installation taking place over 2 years, it's equally divided among the 2 years. If it happens to be 3 years, 30% in the first year, 45% in the second year, and 25% in the third year. 4 years, we are giving a bifurcation, and similarly for the 5 years. It may or may not be exactly equal to these numbers, but these are the normal correlations adopted for the installation of a process plant and whose construction is spread over maybe from 1 to 5 years. So normally we are envisioning that the capital expense would not be going beyond 5 years of expenditure. So going back to the whiteboard, now understanding the discounted cash flows. So the discounted cash flows, the C or the capital cost that I would be recovering would be coming from 3 factors, and it will be having a summation from R is equal to 1 to N. So R basically is the production year where when the production has started, and N is the last year of the production, and then we would have the revenue for a particular year R. Subtracting that would be the fixed capital that is coming in, or the fixed cost for the year R, which is basically a function of like what are the fixed costs that I am putting in, and then would be the variable cost for the year R, and all this cost would be divided by 1 plus I raised to power the year R, which would be varying from 1 to N. So again, to set things into perspective, R is basically the production year when the production has started. N is the final production year. Then R basically is the product revenue. In the year R. FCR is the fixed cost, and VCR is going to be the variable cost. Now what we are going to assume is that like the revenue, the fixed cost and the variable cost remains constant throughout the years. In reality, they would be changing or going up and down as the time proceeds, but for this analysis I am going to assume that all of them remain constant over the years over the operation of plant. So what is going to happen is I would necessarily want to recover all of the capital that is spent on the initial years by the revenue that is generated, and the revenue that is generated would basically be the product revenue minus the fixed and the variable cost that I would be making. Further, I will be making another assumption. So I will be assume that there is no capital build up to full production, which means the production of hydrogen would start as soon as the construction is complete. So if I bring in both the elements together, what I would really want to recover is that C multiplied by 1 plus I, because I am not having any buffer between the completion of the plant erection and the production starting, and this would be equal to the revenue, the fixed cost, the variable cost, and I have taken the summation after this, because these all values I am assuming to be constant over the years. So the only thing that remains in the summation is this formula, wherein the discount or the time value of money is changing over the years. I can further rearrange the terms in this particular equation by the revenue for a particular year would be nothing but the fixed cost plus variable cost plus, now I am rearranging the term, I am having an element k is 1 plus I into C. So what do I really mean by k? So k is basically representing the summation of all the discount rates over the years. So basically that's the sum of a geometric progression. So I believe you all understand what a geometric progression is and how to calculate this sum. So this k would have a value of I 1 plus I raised to power n 1 plus I raised to power n minus 1. So what we have I here is the discount rate and n basically is the number of years, which is basically pertaining to years of operation of a plant. So a typical plant we will aim is operating for roughly 20 years and discount rate could be somewhere around 10%. And further I can also introduce another term which is called k naught, k 1 plus I into C, and to rearrange the terms I will, in the above equation we would have k naught equal to k 1 plus I, and now I am bringing back the original equation where I put in the bifurcation of the capital cost expenses in the initial few years, and this brings in C naught summation of S is equal to 0 till the year P, the breakdown of the cost 1 plus I P minus S. And what I am mainly interested in this factor K naught by C naught. So this is basically the capital recovery factor or the capital charge. So what I am going to do this, so what is the application of this factor? I multiply this factor by the initial capital and this gives me the percentage of capital that I can assume to be happening each year to bring in for the initial capital expense. If you can go back to the slides. So these are some indicative values for the value of k based upon the interest rate and the value of a number of years, which you can check for yourself. So this is how the value of k is going to vary over the change in the interest rate, which is the discount rate, as well as the number of years of operation of plant. So based upon this value of k, you can calculate the factor k naught by C naught, and this is basically the return on capital or the capital charge or the capital recovery factor, which basically would depend upon the number of years of operation as well as the interest rate or the discount rate that you are bringing into picture. So if I am assuming 20-year operation for a plant and a 10% discount rate, possibly this value of k would be 14.32. And in case, because most of these technologies that we are assuming would be proprietary technologies where the industry that is licensing you this technology is also charging some royalty. So I am assuming 2% royalty, this might turn out to be 14.6%. So what I am meaning by this number is that because the capital is happening over the first few years when there is no production, and I would want to see the amount of this capital, how it is spread out during the operation phase. So I multiply this capital with this factor, which is a percentage, to give you what could be the yearly capital expense to make up for the capital that has happened in the initial few years. This is what I mean. So I would want a unit production rate of hydrogen, so that would have yearly expense in the form of feedstock, the yearly expense in terms of the labor and the maintenance, whereas capital is not an yearly expense that happened during the onset of the project. So if I would have to take the capital also as a yearly expense, I divide or I multiply this capital with a factor like 14.32 or 14.6 to get the yearly expense of that capital, so as to get the unit production cost. We can also try to see this with the help of an Excel sheet. So if you can open the Excel sheet. So this is what I have tried to show with the help of an Excel sheet. Suppose I am talking about a number of 3 years of plant construction being taking place, a discount rate of 10%. So the first thing would be calculation of the C1, So if 30% of the expense is happening in the year 1, 45% in the year 2 and 25% in the year mark 3. So the total factors come out to be 1.108. Further, I can assume a value or calculate the value of k from the table above, which is basically the sum of a geometric progression. So if I am assuming for 20 years operation and 10% discount rate, this is the factor, and if I compare the return on capital with these factors, so this is the same formula that has been used, wherein I am just making use of these factors and coming across this value. So if you guys are interested, you can calculate your own values. Again, to show you that the aim here is to divide the capital expenditure equally among the production years of a plant. So basically I would want to divide a one-time expense, which is a capital expenditure, into the operational phase and add that with the feedstock cost and the operation cost to get the unit production cost. Further, if I change this number 1 to 1.02, so herein I am producing a 2% royalty and you will get the number 14.6, which is the same as you would have seen in the slide before. So we have this number 14.32, which is for 20 years of operation and 10% discount rate, and if I am assuming a 2% royalty, it's 14.6 for 20 years operation and 10% interest rate. So these are the type of factors that I will be using in the future calculation. So this is just for your understanding if you would want to go into the derivation where this capital recovery factor or the capital charge or return on capital, these terms are used interchangeably, has been calculated. Further, you need to understand that the analysis that we are doing is pretty on the concept level. So whenever we are trying to do this analysis, it could be on different level. It could be at the concept level, on the feasibility level, and the front end engineering and design level. So again, like the more depth we go into it, it requires more time, more money and more manpower, and further the uncertainty tends to decrease. So what the type of estimates that we will be doing throughout this course will be mainly on the concept level, where we can do just some quick calculations to try to understand how the cost is made build up of. But again, we also need to understand that the errors in the estimate are quite high. Whereas if you would want to go for a much better estimate, you would have to go for front end engineering. That costs a lot, but again, that's not the aim of this course. The current aim of this course is try to get an initial estimate of the different types of expenses that would be used for making up the price of the hydrogen from different sources, as well as the transportation for its future use. So with this, we end the current lecture. Thank you.